So here we have yet another way to draw molecules, a Fisher projection. And Fisher projections are used frequently for sugar. And because sugars have so many chiral centers in them. And in a Fisher projection, the horizontal lines are wedges. And the verticals are dashes. So if you have a Fisher projection that looks like this horizontal line is really on a wedge, and the vertical line is a dash. You can think of it as the carbon is a man wearing a bow tie, and the ends of his bow tie are sticking up. So if we look down here at these, we see that this pair are enantiomers. Remembering that enantiomers are mirror images that are not superimposable. So we have two chiral centers here and here, and at each chiral center, the centers have been reversed. We've got a mirror image. Here's a mirror. And this is not going to be superimposable on top of each other. Here we have diastereomers. Because only one of these are our two chiral centers, and only one of them has been switched. We've got the bromine on the wrong side here to be an enantiomer. So you can convert Fisher projections into our more normal method by choosing one horizontal line and making it a wedge, and choose one vertical and make it a dash. And that will convert your Fisher projection into our wedge and dash form that we're more used to. So let's look at an example. So this is a Fisher projection because it's flat, and we want to change one of the horizontals into a wedge. I'm going to pick this one with the hydrogen because it's going to make naming this thing a lot easier. So we'll make that into a wedge, and we have to pick one of the verticals and make it into a dash, and it doesn't really matter which one we pick. We're going to make that one into our dash. Okay, then we'll need to assign priorities. That's a hydrogen, so that's going to be number 4. Nothing's going to be lower than a hydrogen. This is a carbon, and this is a carbon, and that's a nitrogen. And nitrogen has a higher atomic number than carbon, so it'll be number 2. And then we need to decide between this carbon and this carbon to assign 3 and 4. So this carbon's attached to an oxygen. Actually, it's attached to what we would count as 3 oxygens. We count that double bond twice. So it's number 2. This hydrogen is attached, this carbon is attached to 2 hydrogens and only 1 oxygen. So that makes that number 3. Then we can look at this diagram. We're not going to count the 4. Get rid of it. Go 1, 2, 3. We're going in it looks like we're counterclockwise. And that would make it S, except that the lowest group is toward me. Except that number 4 is toward me. So I'm going to reverse it, and it's going to be R. Because we're looking at the back of the molecule. So let's do that again. Again, we've got this is our chiral carbon right here. We're going to make this, I'm going to make the hydrogen a wedge because that makes it easier for me. I'm all about making it easy. And we can make either one of these dashes, it doesn't matter. We'll make that one the dash. We'll need to assign priorities. So we have an oxygen, carbon, hydrogen, and a carbon. So the oxygen is the highest atomic number, so it gets 1. Now we need to decide between the two carbons. This carbon only has hydrogens attached, and this carbon has an oxygen attached. So it will be number 2, and we'll make this one number 3. And of course the hydrogen is number 4. So I've got the same situation. I've got the number 4 group toward me. I can look to see which direction we're going, and we're going in a clockwise direction. So I'm going to write the same thing as I did before. It looks like it's an R, but that hydrogen is toward me, or let's say number 4. Number 4 is toward me, so it's really an S. We'll do this last one real quickly. We're going to put a wedge here, and we can make either of these two dashes. It doesn't matter which one we pick. And then we need to assign. The oxygen is going to be number 1. Got 2 carbons. Each carbon here is attached to 2 hydrogens and then 1 oxygen here and a carbon here. The oxygen is higher, so it goes there, and there's 3, and here's number 4. So we're going to change colors. It looks like it's R because we're going in a clockwise direction, but number 4 is toward me, so it's an S. Okay? The last thing I want to talk about on this video is that you can have chiral compounds that lack a chiral center. If you've got 2 double bonds next to each other, as in this conformation, these are mirror images that are non-superimposable, but we don't have any chiral compounds. So these are allotrope isomers, and they result from hindered rotation of a single bond.